That's very satisfying. That's fine. Come on, I'd like to do that.
I'm just gonna take it for my classroom.
That's random.
Any questions?
Yeah, we did. We left it.
Stick that silent. So let's start the next session. First of all, thanks, Clement, for letting me ring the bell. It's amazing. So, next speaker, I was a bit afraid of having to pronounce the name, but apparently I'm allowed to say Ben. Great. So he's going to talk about approximation and semi-string.
Yes.
Yours.
Thank you.
Hello, everyone. Today's talk is based on our recent research paper called Toward Optimal Semi-Streaming Algorithm for 1+ε approximate maximum matching. And this paper is by my advisors, Lobodan Mitrović, and our collaborators, Anish Mukherjee, Piotr Stankowski, and I am today's presenter, Wen-Horng Sheu from UC Davis. And the problem we consider in this paper is the maximum matching problem. The input of this problem is an unweighted graph, and a matching is a set of edges that do not share any endpoint. And the goal of this problem is to find the largest matching. And this problem has been extensively studied in many different settings. Since 1957, people have been considering how to solve it in polynomial time. And also, there are some research groups studying how to estimate its size, how to dynamically maintain matchings. And today we are considering one of the settings called the semi-streaming model. And this is also a line of research that has been explored by several papers. And let me state the definition of semi-streaming setting. So in this setting, we assume that the graph is very large and we don't have random access to that input graph. And the edges of this graph is presented as a string, and we can read the string and the edges will arrive in arbitrary order. And reading the string once is called a pass. And the algorithm can use big O of n times polylog memory, and it can read the string for multiple passes. And the goal of this setting is often to minimize the number of passes to solve some problem. And the problem we are going to consider today is to find a 1+ε approximate maximum matching on general graphs. Is there any question about this? Okay. So for this problem, a really surprising result is that a constant number of passes is achievable. In 2005, McGregor had an algorithm that solved this problem in 1/ε to the power big O of 1/ε passes. And when epsilon is a constant, this is constant number of passes. And since then, the dependence on epsilon has been improved. And so the research of this problem often distinguished between two classes of graphs. One is bipartite and general. And we also consider two families of algorithm. The first family is the constant path algorithm, where the path complexity only depends on 1/ε. And it's also the focus of this talk. But there is another family of study called epsilon efficient algorithm, where the path complexity can depend on log n and 1/ε. And we try to reduce the dependence on 1/ε. So for bipartite graph, poly 1/ε passes has been known since 2009 by Eggert, Kleeman, Monsterman, and Srivastava. And this is a research history for this problem. The first algorithm is McGregor's algorithm that solved this problem in exponential number of passes. And then some authors have discovered poly 1 over epsilon passes algorithm that runs in 1 over epsilon to the power 8 passes. And there have been improvement for this problem. And the current best algorithm is by Assadi, Liu, and Tajun. In 2021, they had a 1 over epsilon squared pass algorithm. But for general graph, the situation is very different because poly 1 over epsilon pass algorithm is only known recently by the paper of Fischer, Mitrović, and Uitto in 2022. And this is the research history for general graph. Again, the first algorithm is by McGregor, which runs in exponential number of passes. And later, there are some algorithms for this, new algorithm for this problem, but they either have dependence on log n or has exponential dependence on 1 over epsilon. Until 2022, FNU's paper made a breakthrough to propose a 1 over epsilon to the power 19 algorithm, reducing the path complexity to poly 1 over epsilon. And later, there are some researching how to solve this problem on weighted graph. But for unweighted graph, the current best algorithm is FNU's algorithm. So the research paper we are going to talk about, sorry. So there's a huge gap between bipartite and general graphs. So for bipartite graph, there has been a 1 over epsilon to the power 2 pass algorithm, which is simple and elegant. But for general graph, the best algorithm is still 1 over epsilon to the power 19. Okay, so the result we are going to talk about today is a new algorithm that runs in 1 over epsilon to the power 6 pass. And the main focus of this work is to bridge in the gap between bipartite and general graphs. And also we provide a simpler approach and a simpler analysis for this problem. It's still not very simple, but it's simpler. So a remark about some other models. So our semi-streaming algorithm can also be simulated in other distributed computational models. So this result also implies improvement of random complexity in the MPC and CONGEST model by a factor of epsilon to the power minus 13. So, let's to present our algorithm, let's first look at a simpler algorithm, which is for bipartite graph, and it's based on EKNS algorithm for bipartite graph. So some definition about matching. We say an unmatched vertex is a free node, and an alternating path is a path alternates between matched and unmatched edges. And an augmenting path is an alternating path from one free node to another. So this example shows an augmenting path, and it's also an alternating path. The starting point of this algorithm is to find short augmenting paths. This is a regular standard approach that has been used in several papers, and it's based on the following property. The property is that suppose that you have a matching N, and you have an inclusion-wise maximal set of short augmenting paths. Here, short means that the length of the augmenting path is at most 2 over epsilon. And if you find that this maximal set of short augmenting paths is smaller than some threshold, then you certify that the current matching is a 1+ epsilon approximate matching. So in short, a small maximal set of short augmenting paths can certify a 1+ epsilon matching. So this property motivates an approach to solve the problem. That is to keep finding inclusion-wise maximal set of short augmentations. And if it is small, we certify that the current matching is a 1+ epsilon approximation. If it is large, we use this set to augment the current matching. So this is the approach that is used in this algorithm. And the idea of this algorithm is to execute truncated DFS from free nodes. So you can imagine that you run a parallel and multi-source DFS from all the free nodes. And this DFS search is to find the short augmenting path. So we will truncate the DFS tree in the depth of 1 over epsilon. because we only want to find augmenting path of length 1 over epsilon. So truncated means that the depth is at most 1 over epsilon. So let's look at some details and an example. So this is a graph that we will run our instance on. And for each match age, we will maintain a distance label. Initially, the distance label is initialized to infinity. And the meaning of this distance label is that the current shortest alternating distance to this match age. And each free node will maintain an active path, which is its DFS search path. And we try to extend this DFS search path and find short paths to these match ages. In each path, we try to simulate one step of DFS and to extend the active path of each free node by a length 2 path. This is done by scanning the unmatched ages and see whether we can use this unmatched age to extend the current active path of some free node. And so for example, for this vertex U, when we scan this unmatched age, you will find that it can use this unmatched age to reach a matched age. And in this case, we will extend its active path to include this match age. Now, this match age can be reached by some free node using distance 1. So we set its distance label to 1. The distance is calculated as the number of match age in the path. And as in DFS, if we find that in a whole path, some paths cannot extend, we will let it backtrack. So like this free node U, in the first pass, it can extend to this match age. In the next pass, it finds that this is stuck, so it backtracks. And this free node U can further extend to reduce the distance label of some other age. And we only perform extension if we can reduce the distance label of some match age. Also, there is a special operation called overtake operation in this algorithm. So this overtake operation happens when a free node U can find a shorter path to some match age, but this match age is already in another active path. In this case, this free node U will extend through this shorter path and take over this match age. So in this example, this match age was in the active path of V, but now it's overtaken by the free node U, and its distance label is reduced to 1. And we only allow overtake if we can reduce the distance label. So there are some details about this overtaking operation that we will not go into, but the idea is that we always allow the shorter path to reach a matched age because we want to find short augmenting paths. Any path that can be found by V also can be found by U because U has a shorter path. And in the last pass, this free node U finds an augmentation, and we will remove this augmenting path and let other free nodes continue the search. For the analysis of this algorithm, we will not go into details, but they showed that this algorithm can be implemented in probably 1 over epsilon passes, and it finds an almost maximal set of short augmenting paths. The almost means that its size is almost as large as some maximal set of short augmenting paths. And they use this algorithm to solve, to find 1+ epsilon matching in bipartite graphs by finding this maximal set of short augmenting paths. But this type of algorithms will face some challenge in general graphs because when there are odd cycles, free nodes can block itself during its DFS search. So let's look at one example. So in this example, there is an augmenting path, and our goal is to find this blue augmenting path. But there may be some other edges in this path. Like there are 2 odd cycles in this path. And this free node U may not search through this augmenting path using the direction we want. It may first take a shortcut using this odd cycle and traverse the path in a reverse direction. And then it again takes into another odd cycle and traverse using forward direction again. At this moment, this free node U is blocked by itself because it cannot extend to the right. It has already occupied some edge to the right. So this free node U will eventually backtrack, but it will leave this distance label because it already explored some match edges. But when it tries to extend over the correct direction to find this augmentation, it will again be blocked because it cannot find a shorter path for this match edge, so it cannot extend through this path. So in this case, because of a cycle, this DFS search can block itself. And this augmenting path is never found. And previous algorithm handle this case by storing the full search history for each free node. So in FNU's paper, they try to store all the visited vertices and edges in the part of graph visited by you. And they will use this information to detect odd cycles. And when they detect odd cycles, they will try to jump through these odd cycles. This is a rather complicated approach that we will not go through today. So I want to introduce our approach, which offers a simple way to handle these odd cycles on general graph. Any questions so far? Okay. So our idea is to maintain alternating trees. In our algorithm, each free node will grow an alternating tree. And an alternating tree is a tree such that the root vertex is a free node. And every root to leaf path is an alternating path. And these trees will be vertex disjoint. And every free node will have one tree. And again, we will have an active path, which is our DFS search path in this tree. So you can as well think of this alternating tree as a DFS search history, the DFS search tree. And we will partition the vertices, we'll classify the vertices of this alternating tree into two classes. The vertices in the outer layer, the vertices in the even layers are called outer vertices. And in the odd layers are called inner vertices. In particular, the root vertex is an outer vertex. And each inner vertex will only has one child that is matched to itself. And we will try to extend these alternating trees. And the way we extend is that we will read all the edges from a string. Let's say we read edges W and W from W to V. And we only focus on the edges that can be used to extend an active path. So in this example, the active path stops at W, and we read an edge from W to V. So there are some cases. The first case is that if we find that this vertex V is not in any tree, this means that this is a match edge that is not visited by any tree so far. Then we just include it into our alternating tree. And we set its distance label as the depth of this tree, the depth of this match edge. And the second case is when this vertex V is in another tree, and it is an inner vertex. In this case, we try to see whether we can update the label of the matched edge incident to this inner vertex. If we can update its label, it means that we find a shorter path to this matched edge. Then in this case, we will perform overtaking operation to overtake this matched edge to our tree. But the special thing is that we will also overtake the whole subtree under this vertex V. And so that after this overtaking operation, the two trees still remains to be alternating trees. And the third case is when V is an outer vertex of another tree. In this case, we can show that the tree path to this W and the tree path to this V form an augmenting path between these two trees. So we will record this augmenting path and remove both trees. The reason we remove the whole trees is because we don't know how to handle this DFS search history. We don't know how to handle updates labels so that it's still meaningful because they cannot be visited by these free nodes anymore. So we don't know how to handle them, so we just remove all of them from the graph. So it may be an interesting research. Oh, okay.
Do you have a bound on the degrees of the tree? Or?
No, we will not have a bound on degree of the tree, but we will have a size bound on the degree, on total size, total number of vertices of the tree. Yes. So it may be an interesting direction to handle, like how do we modify this operation so that we do not destruct the whole tree. But let's get back to the algorithm. So the final case is when V is again an outer vertex, but from the same tree. In this case, this edge forms an odd cycle inside of the tree. So we somehow have to handle this odd cycle. And the way we handle this odd cycle is by Brasson contraction. So this is a property proved by Edmond in 1965. If we have an alternating tree T, and we find that an edge connects two outer vertices of tree T, then this edge connecting these two vertices will form a Brasson. And a Brasson is a subgraph such that it forms an odd cycle with exactly one unmatched vertex, like this Brasson B in this example. So the way we handle this odd cycle is that we just contract them. We just contract this odd cycle into a single vertex in this tree. And it can be shown that by contracting such a Brasson, this tree T will remain an alternating tree.
So you need to contract in terms of later you want to form a matching. That this will be a single matching edge, or
this will be a single vertex. And later, if we find an augmenting path between two free nodes and some of the nodes are Brasson, we will look into the Brasson and replace each Brasson by an even length alternating path, so that this is still an augmenting path. So this is a very simple and natural way to grow alternating trees. We only have 4 operations, either to extend or overtake, or we augment them to remove both of the trees, or we contract some Brassons in the tree. Only 4 operations to grow these alternating trees. It's very simple. So to analyze this algorithm, we have to show that it can find an almost maximal set of short augmenting paths. Here, almost means that its size is close to some maximal set of short augmenting paths up to a factor of poly 1/ε. But this part is very technical, so we will not go into this part today. Any questions so far? So instead, I will go into a rather interesting part of this whole proof. So this part is to show that a tree cannot grow beyond poly 1/ε. We cannot allow any tree to grow too large. And the reason we have to prove this in our correctness proof is that when we find an augmenting path, we will remove 2 trees from the graph. And if the 2 trees are too large, this can destroy a lot of other augmenting paths. So we find a single augmenting path between the 2 trees, but we remove a lot of other matched edges and vertices, which can intersect other augmenting paths. So we want to show that this operation will not remove too many vertices, so we do not destroy too many augmentation used when we find one augmenting path. Does that make sense? So the idea we used here is that in our algorithm, we will put a hard limit on the tree size. So a tree will be frozen when its size reaches some parameter limit set equals to 1/ε². So here, frozen means that we do not allow it to extend anymore. We do not allow it to overtake or extend or do anything else in the future because its size has grown into too big. Its size has become too big. So is this enough so that no tree can go beyond limit, this parameter limit? Sadly, the answer is no, because there can be another tree that overtakes this tree that has already grown into a limit, the size of limit. So if you have 2 big trees, both of them are of size around limit, and one overtakes another, then the new tree will become size of 2 times limit. And this overtaking operation can keep going on. If there is a third tree that also has size limit and it overtakes this big tree of size 2 limit, you get an even bigger tree of size 3 times limit. And this chain of overtaking operation can keep going on until we grow a tree of very large size. So the idea, any question?
Hello, I have a question. That is, these frozen trees can backtrack or we cannot backtrack?
These frozen trees will not backtrack. Other questions? So the idea we use to bound the tree size is that we show that this chain of overtaking operation is at most of length 1 over epsilon. The intuition behind it is that when we try to overtake a big tree, let's go back to the first example. When we try to overtake a big tree, we have to reduce the label, the distance label of its root. And again, when the third tree tries to overtake a tree of size 2 times limit, it again has to reduce the distance label of the root of this big tree. In particular, it cannot overtake any edge inside of this yellow subtree because it will not have size 2 times limit. It also cannot overtake this part because it will not have size 2 times limit. It has to overtake the root so that it can overtake the whole part of size about 2 times limit. So whenever an overtaking operation happens, the overtaker's label must be smaller than the overtaken tree's label. So in this chain of overtaking, there will be a sequence of, if there are a sequence of trees overtaking each other, there's the label of the root of these trees will form a strictly increasing sequence. And since we bound the distance label by 1 over epsilon, this sequence can have length at most 1 over epsilon. So the final tree can only has total size 1 over epsilon times limit. So this is the interesting part of our analysis that bound the tree size. So the presentation of this algorithm will stop here, and here are some open questions. So the first open question is that whether we can improve the poly 1 over epsilon dependence of this algorithm furthermore, and whether we can further simplify the current approach. And also another interesting open question is that whether we can do B matching in poly 1 over epsilon passes in general graphs. So in bipartite graph, poly 1 over epsilon has been known, but in general graph, there is still no B matching algorithm that runs in poly 1 over epsilon pass. Only exponential 1 over epsilon pass algorithm exists. So that's the end of the talk. Is there any questions?
So for B matching, do you want n B as space, or is that like one B matching and one OT line as space?
Okay, the space goal is the summation of all B values. So the reason to put this goal is because the output size of B matching can be at most, can be at most the sum of B values. And so we put this goal as our space constraint because that's the minimum space required to output the solution.
So speaking of space, like how big epsilon factors do you hide in the?
This algorithm in a space. Oh, okay. It's not large. It's also 1 over epsilon to the power 6. But that big O hides a rather big constant, like 1 million. Yeah, in the path complexity. But I think that can be improved by a more careful analysis. It can probably be down to like 10 or 100. I think that's reasonable.
Yeah, why become 1 million?
Oh, because there are several steps of the analysis, and in every step we do not we introduce a factor of 2 or 3 so that we can have a simpler analysis. So all those steps will like multiply each other. So if you have a lot of factor of 2, it becomes like 1 million. But those factors of 2 can be removed by more careful analysis. I think that's only the problem of analysis.
All right. So in the interest of time, let's thank Ben again.